movie's end, a group of students rounds up 5 kilograms of silverware to melt into silver bullets so they can stop the werewolf. Only the student in charge leaves the lab to go surfing, and the silverware gets overheated and turns into a gas. The question is, how many joules does it take to turn the 5 kilograms of silver place settings from a solid at 20 degrees Celsius into a gas at 2300 degrees Celsius?
Hey, what are we gonna do about the werewolf? Why would a werewolf come to Hawaii?
Yeah, I don't even know. I'd heard this happened last summer, and it was just old Mr. Johnson.
Guys, what are we gonna do about the werewolf?
Hey, you know what? Who cares? Let's surf!
Okay.
We're going to need a lot of information on silver to do this problem, including its melting and boiling points, heat of fusion and vaporization, and its specific heat capacity.
First, we're given that the melting point of silver, when solid silver turns into a liquid, is 962 degrees Celsius. The boiling point of silver, when liquid silver turns into gas, is 2,212 degrees Celsius.
Silver's heat of fusion is 88 kilojoules per kilogram. Its heat of vaporization is 2,335 kilojoules per kilogram.
And lastly, silver's specific heat capacity as a solid is 0.235 kilojoules per kilogram degrees Celsius. As a liquid, it's 0.278 kilojoules per kilogram degrees Celsius. And as a gas, silver's specific heat capacity is 0.193 kilojoules per kilogram degrees Celsius.
Before we start doing anything with those numbers, let's make a graph to get a better picture of what happens when 5 kilograms of silver at 20 degrees Celsius is heated until it becomes a gas at 2300 degrees Celsius.
Let's label the x-axis heat in joules and the y-axis temperature in degrees Celsius. As heat is added, the temperature rises to 962 degrees Celsius. We'll call that stage 1. Since that's the melting point of silver, then silver undergoes a phase change and the graph plateaus. The temperature stays the same because during a phase change, heat stops raising the temperature and works instead on changing the phase from solid to liquid.
So at 962 degrees Celsius, we find both solid silver and liquid silver. This is in stage 2. In stage 3, the temperature begins to rise and the silver is only in liquid form.
Then, at 2,212 degrees Celsius, the graph plateaus again, because the temperature is at the boiling point of silver. This is stage 4, so the silver undergoes a phase change where the temperature stays the same and we find a mixture of liquid and gas. Then at stage 5, the temperature rises again and we just find a gaseous silver. So by the time it hits 2300 degrees Celsius, silver is a gas.
We can calculate how many joules it takes to heat 5 kilograms of silver at 20 degrees Celsius to 2300 degrees Celsius by calculating the heat needed for each stage, then adding up our results at the end. So let's start with stage 1.
To find the amount of heat in stage 1, we need to see how much heat it takes to change the temperature of that silverware from 20 degrees Celsius to 962 degrees Celsius, the melting point of silver. To do this, we use the equation heat, Q, equals the mass of silver, M, times its specific heat capacity, times the change in temperature, delta T. We use this equation because stage 1 is where there is only solid silver, with no phase changing occurring.
So we have that Q equals MC times delta T. And guess what? We have all the information we need to fill in the equation. The silver's mass is 5 kilograms. Its specific heat capacity as a solid is 0.235 kilojoules per kilogram degrees Celsius, and the change in temperature is the final temperature minus the initial temperature. That's 962 degrees Celsius minus 20 degrees Celsius, which is 942 degrees Celsius.
Filling in, we see that 5 kilograms times 0.235 kilojoules per kilogram degrees Celsius times 942 degrees Celsius equals 1,107 kilojoules. Notice how all the units cancel and we're left with just kilojoules. So, it takes 1,107 kilojoules of heat to complete stage 1 and raise the silver's temperature from 20 degrees Celsius to 962 degrees Celsius.
In stage 2, we need to change the phase of the silver from solid to liquid. So we have to use a different equation than what we used for stage 1 because a phase change occurs. We use the equation where heat, Q, equals mass, M, times latent heat, L. It's the latent heat that tips us off that this is the right equation, because latent heat is the heat necessary for a phase change.
Since this is the stage where we find solid silver and liquid silver together, we have to use the heat of fusion, L sub F. Remember, the heat of fusion is what we use when the substance is changing from solid to liquid. So, Q equals little m times L sub F. We were given mass and the latent heat of fusion for silver, so let's fill in what we've got. Q equals 5 kilograms times 88 kilojoules per kilogram, which is 440 kilojoules. That's how much heat it takes to complete stage 2.
In stage 3, silver is a liquid, so the specific heat capacity is different, and the temperature rises from silver's melting point, 962 degrees Celsius, to silver's boiling point, 2212 degrees Celsius. This time we use the equation Q equals mc times delta T, because there's no phase change and no latent heat hanging around. We know the mass is 5 kilograms and silver's specific heat capacity as a liquid is 0.278 kilojoules per kilogram degrees Celsius.
So, we plug those into our equation and we get Q equals 5 kilograms times 0.278 kilojoules per kilogram degrees Celsius times the change in temperature, 2212 degrees Celsius minus 962 degrees Celsius. Multiplying all that out, Q equals 1,738 kilojoules, which is the amount of heat it takes to complete stage 3 and raise 5 kilograms of silver from its melting point to its boiling point.
In stage 4, we have both silver liquid and silver gas. In order to change the phase in stage 4, we go back to our equation Q equals m times L sub V. So the amount of heat equals mass times the latent heat of vaporization for silver, or 5 kilograms times 2,335 kilojoules per kilogram. There's that latent heat again. Remember, phase change, latent heat equation. Now we can plug in what we've got and crank out an answer.
We interrupt this example for an important phase-changing announcement. Remember, since we're dealing with a phase change from liquid to gas, we use the latent heat of vaporization, not the latent heat of fusion, which we use when we change from solid to liquid. They're not the same thing. Now, back to our example already in progress.
We have Q equals m times L sub V. Q equals 5 kilograms times 2,335 kilojoules per kilogram, which is 11,675 kilojoules. So that's the heat required for stage 4, where the liquid silver changes completely to a gas.
In this last stage, silver is in a gaseous state. The temperature of the silver rises from its boiling point, 2,212 degrees Celsius, to 2,300 degrees Celsius, the temperature given in the problem. To find out how many joules of heat it takes to complete stage 5, because there's no phase change nor latent heat, we go to our equation Q equals mc times delta T.
Now we just fill in our numbers. Q equals 5 kilograms times the specific heat capacity of silver gas, 0.193 kilojoules per kilogram degrees Celsius times 2,300 degrees Celsius, minus 2,212 degrees Celsius, and we get 85 kilojoules, which is the amount of heat it takes to complete stage 5, and heat the gaseous silver from 2,212 degrees Celsius to 2,300 degrees Celsius.
Now that we have the amount of heat it takes to complete all the stages, we can figure out the total amount of heat it takes to heat 5 kilograms of silverware from a solid at 20 degrees Celsius to a gas at 2,300 degrees Celsius. We do this by adding together the amount of heat we found in each of the 5 stages, which looks a little something like this.
Stage 1, 1,107 kilojoules. Stage 2, 440 kilojoules. Stage 3, 1,738 kilojoules. Stage 4, 11,675 kilojoules. Stage 5, 85 kilojoules. Now add these up and we get that it takes 15,045 kilojoules of heat for silver to go from stage 1, a solid at 20 degrees Celsius, to stage 5, a gas at 2,300 degrees Celsius.
Well, there you have it. Now that that's done, I'm going to watch the rest of my movie while you learn how heat is transferred.
I I can't believe this is happening. This could be the last day of our lives.
Yeah, this has been one crazy summer.
Hi, guys! Oh, hey, it turns out that he wasn't a werewolf at all. He was just going through a phase change. We call it acne.
Cool, let's surf!
Okay.
Section C. Conduction, convection, and radiation.
Heat is transferred three ways: conduction, convection, and radiation. If we stand near a campfire, we can show you examples of all three means of heat transfer.
Suppose you stick a metal fireplace poker directly into the fire and you sit there, holding on to the other end. Well, soon you'll be feeling pain in your hand because the metal will have heated up. This is because of conduction. Conduction is heat transfer via the collision of molecules.
When the end of the poker is in the fire, it gets heated, and the molecules at the end acquire more and more kinetic energy. Then, the molecules move faster and faster by vibrating around their equilibrium positions. So, while they're vibrating, they bump into their neighbor molecules, and that gets the neighbors excited.
Then, those neighbors bump into their neighbors, and so on and so on. After a while, the molecules at the end that you're holding finally get the energy, and they start to vibrate and become hot. And then, heat is transferred to your hand, and that's where the pain comes in.
That was conduction. Now we're going to talk about convection. Convection is the transfer of heat due to the mass movement of heated molecules. An example of this is when you hold your hands over a fire and your hands warm up.
Your hands start to warm up because the air directly above the fire heats up, expands, and then rises. The air then flows by your hands, and as it does, the air warms your hands.
Now, let's suppose you're sitting next to the fire, but not in it. So you don't experience conduction or burning. And you're not above it, so you don't experience convection. You're just sitting there, feeling the heat. That's because you're absorbing radiation.
The fire, like the sun, is emitting light, both visible and invisible. Some of the invisible light is heat in the form of infrared radiation. This is how the sun heats us, and how the fire heats you when you're sitting near it, but not in it or above it.
So, the next time you're with a group of friends roasting marshmallows by the fire, you can tell everyone how they're being affected by radiation.
Okay, now that we know how heat is transferred, let's look at how heat and work go together.
Section D. Heat and work.
When we talked about work before, we talked about the work done by large objects. Now, we're going to talk about the work done by gases, like the internal combustion engine, where the expanding gas from burning gasoline pushes a piston.
Let's suppose we have some Einsteinium gas, and suppose that it's in a container. Now suppose that the top of the container is movable. In fact, it's a piston, so it can move up and down easily. When the piston goes up and down, the volume of the gas changes. The piston goes up because the Einsteinium gas is doing work on it.
The gas does work by applying pressure, which is force per unit area. So if the gas gets heated and expands, it will put pressure on the piston until it reaches the volume where it wants to be.
So the pressure does work on the piston, increasing the volume and causing the piston to move, thereby doing work. Believe it or not, there's a cool equation that puts this relationship in a form we can put to good use. Here it is. The change in work, delta W, equals the pressure of the gas, little p, times the change in volume, delta V. So, delta W equals little p delta V.
If work is measured in joules, then the unit of pressure is the Pascal, capital P, little a, which is 1 Newton per meter squared, and volume is measured in meters cubed. But because the numbers we work with are so large, it's probably easier to measure work in kilojoules and pressure in kilopascals.
So, if we have steam kept at a constant pressure of 120 kilopascals, the work done by the gas is 240 kilojoules, and its initial volume was 1.03 meters cubed, then what's the final volume of the steam?
Okay, we know that the change in work equals pressure times the change in volume. Delta W equals P times delta V. We've already got work, pressure, and the initial volume, so we can now solve for the final volume.
Again, our formula for work is delta W equals P times delta V. Delta V equals the final volume minus the initial volume. So, delta W equals P times the quantity V sub F minus V sub I. Isolating V sub F, we get V sub F equals delta W over P plus V sub I. Filling in what we've been given, V sub F, the amount of work done by the steam, equals 240 kilojoules, divided by the constant pressure of the steam, 120 kilopascals, plus the initial volume of the steam, 1.03 meters cubed. Work that out and we find that the final volume of the steam is 3.03 meters cubed. See how that worked? To do its 240 kilojoules worth of work on the piston, the steam expanded from a volume of 1.03 meters cubed to a volume of 3.03 meters cubed.
The temperature of a substance stays the same during a phase change. The latent heat of a substance is the amount of heat needed to turn 1 kilogram of it from one phase to another. And heat equals mass times the substance's latent heat, or Q equals mL. When a solid turns into a liquid, that's called the heat of fusion. And from a liquid into a gas, that's the heat of vaporization of a substance.
Heat is transferred by conduction, convection, and radiation. Conduction is heat transfer via the collision of molecules. Convection is the transfer of heat due to the movement of a heated substance. And radiation is the transfer of energy through the space between those molecules.
And the change in work done by gases is directly proportional to the pressure and the change in volume of the gas, or delta W equals P delta V. And that's it.
Part 6, Thermodynamics.
Up to now, we've been talking about heat. Well, this is where it all pays off. Thermodynamics is the branch of physics that deals with the transformation of heat into mechanical energy. And it's that mechanical energy that gets us going.
We're going to go over the first law of thermodynamics, the second law of thermodynamics, heat engines, and entropy. So let's get rolling.
Section A, the first law of thermodynamics.
When we talk about thermodynamics, we need to make it clear what the difference is between heat and work. Heat is the transfer of energy due to the change in temperature, and work is the transfer of energy that is not due to a change in temperature.
Both the heat and work affect the internal energy of the system. The internal energy, logically represented by a capital U, is the total energy of the molecules of the system.
So when a substance undergoes a phase change, internal energy changes, but with no change in temperature.
And if the system does work, this lowers the internal energy of the system, because that energy is going somewhere else. Like when you lift up something heavy, you transform energy. And it works the other way too. If heat is added to the system, its internal energy increases. This relationship is the first law of thermodynamics.
The first law of thermodynamics states that the change in the internal energy of a system, delta U, equals the heat, Q, added to the system minus the work, W, done by the system. So delta U equals Q minus W. Look how this works.
If heat is removed from the system, Q, the heat added, is negative because we're taking heat away or adding a negative amount of heat. Therefore, the internal energy of the system decreases. Now, if work is done to the system, then W is negative, because the system is not doing work, it's taking work in. Therefore, the internal energy increases. Now, you can see that the first law of thermodynamics is just a generalized statement of the law of the conservation of energy, recognizing that heat is just another form of energy.
So, heat and work have to do with energy going in and out of the system. The change in the internal energy of the system is how the internal energy reacts to this transfer.
We can look at a few different situations to see how the first law of thermodynamics can be used. First, let's look at a gas where the volume is kept constant. This is called an isovolumetric process.
So, if the volume of the gas is kept constant, then the change in the volume, delta V, equals 0, because delta V equals V final minus V initial. So, if there's no change, then V final equals V initial, and the difference is 0. So delta V equals 0.
And remember when we talked about gases doing work, we learned that the change in work, delta W, equals pressure, P, times the change in volume, delta V. So since we already found out that delta V equals 0, then the change in work done by a gas at a constant volume also equals 0, because delta W equals P times 0, which equals 0.
So, for an isovolumetric process, the change in work equals 0, so no work is done by the system or to the system. Not much of a process, is it?
Now, to figure out how an isovolumetric process affects our equation for the first law of thermodynamics, delta U equals Q minus W, we just fill in that work equals 0, and we get that delta U equals Q. So, for an isovolumetric process, the increase in the internal energy of the system equals the heat added to the system.
So, that's an isovolumetric process. Now, suppose we have a system where the pressure is constant, but the volume can change. This is called an isobaric process.
So, if delta U, the change in the internal energy of the system, equals Q, heat, minus W, work, and W equals P times delta V, then substituting P delta V in for W, we get that delta U equals Q minus P times delta V. This is the equation we would use to find the change in internal energy for an isobaric process.
The third process we're going to learn about, which involves the first law of thermodynamics, is an adiabatic process. This is when we have a system where no heat is added.
Delta U, the change in internal energy, equals Q, heat, minus W, work. If no heat is added in an adiabatic process, the heat, Q, equals 0. And delta U equals 0 minus W, or delta U equals negative W. So for an adiabatic process, the increase in the internal energy of the system equals the negative of the work done by or to the system.
All right, enough of the equation talk. Let's do a problem.
Suppose we have 1.0 kilograms of liquid water at 100 degrees Celsius, occupying 0.001 cubic meters, and subject to a pressure of 1.013 times 10 to the 5th pascals. When the water is boiled, it becomes steam at 100 degrees Celsius, with the steam occupying a volume of 1.7 cubic meters. For our problem, first, figure out what kind of process this is. Then, if we're given that the latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram, figure out what the change in the water's internal energy is.
Before we tackle this problem, let's sort out all the information that the problem has dumped on us. We have the mass, m, of 1.0 kilograms. We have temperature, T, of 100 degrees Celsius. The initial volume of the water, V sub I, is 0.001 meters cubed. Pressure P is 1.013 times 10 to the 5th pascals. The final volume of the steam, V sub F, is 1.7 cubic meters, and we have water's latent heat of vaporization as 2.26 times 10 to the 6th joules per kilogram.
Wow, that's a lot of information. Now that we have it all down, let's first figure out what kind of process this is. Remember, when we're dealing with the first law of thermodynamics, we've got 3 types of processes to choose from: isovolumetric, isobaric, and adiabatic. Well, for starters, the volume of the water changes, so it can't be an isovolumetric process because that's the process where the volume is constant. Also, the water changes from a liquid stage to a gas stage, and to undergo a phase change, we must add heat. So this process can't be adiabatic because that's the process where no heat is added. But the pressure in our problem is constant, so it must be an isobaric process.
The problem is asking us to find delta U, the change in internal energy of the water. And since we weren't given work, we can use the equation that we derived for delta U in an isobaric process. That's delta U equals Q minus pressure, P, times the change in volume, delta V.
Let's look at what we were given and see if we have everything we need to plug in those numbers and crank out an answer.
We have pressure P and the initial and final volumes, so we can find the change in volume, delta V. What we don't have is Q, the amount of heat added.
To find Q, we have to go back to what we learned about phase changes. In our problem, liquid water boils and turns into a gas, so it goes from the liquid stage into the gas stage. And when a substance goes from liquid to gas, we find the amount of heat added to the system by multiplying mass times the latent heat of vaporization, or Q equals m times L sub V. Remember that when we talked about phase changes?
We were given the water's mass of 1.0 kilograms and water's latent heat of vaporization of 2.26 times 10 to the 6th joules per kilogram. So now we can solve for the amount of heat added. Q equals m times L sub V. So, filling in the numbers, Q equals 1.0 kilograms times 2.26 times 10 to the 6th joules per kilogram, or Q equals 2.26 times 10 to the 6th joules.
Now that we've found the amount of heat added in order to turn the water from a liquid to a gas, we can go back to our equation for finding the change in the internal energy of an isobaric process. Delta U equals Q minus P delta V. Now we've got everything we need to fill in our numbers and find the change in the water's internal energy.
Delta U equals Q minus P delta V. Remember, delta V equals V final minus V initial. So, delta U equals Q minus P times V sub F minus V sub I. Q, the amount of heat added to the water, is 2.26 times 10 to the 6th joules. P, the pressure the water is subjected to, is 1.013 times 10 to the 5th pascals. V sub I, the initial volume of the water in its liquid state, is 0.001 meters cubed. And V sub F, the final volume of the water in its gaseous state, is 1.7 meters cubed.
Filling in our numbers, we get that delta U equals 2.26 times 10 to the 6th joules minus 1.013 times 10 to the 5th pascals times 1.7 meters cubed minus 0.001 meters cubed. Working all this out, we get 2.1 times 10 to the 6th joules. So, the change in internal energy when 0.001 cubic meters of water is changed to 1.7 cubic meters of steam is 2.1 times 10 to the 6th joules. So, we found out the change in internal energy. You might be wondering why we were given the temperature if we didn't use it in our calculations. You might be suspicious, certain it was thrown in there just to mess with your head. To send you in the wrong direction, never to return. Well, it was actually important to know that the water was at 100 degrees Celsius, its boiling point, because that told us that it was going through a phase change. And now it's time to move on to
Section B, the second law of thermodynamics.
When we're working with the second law of thermodynamics, there are many types of processes that a system can go through. These can be divided into two groups, reversible and irreversible processes. A reversible process is one that, after it's finished, can go backwards and end up where it started. An irreversible process, on the other hand, is a process that can't go back and restore itself. All processes that occur in nature are irreversible. For example, if in a fit of rage you drop your mom's favorite vase on the floor, it'll shatter into 1,000,000 pieces. Now suppose those pieces suddenly gathered themselves up and flew back into their original form. You'd probably think that you were going crazy.
For your mom's sake, it might be nice if breaking the vase was a reversible process, but it's not. It's irreversible.
Another example of an irreversible process is if we put a hot object, like this famous athlete, into direct contact with a cold object, like this frigid metal rod. Heat energy flows from the hotter object to the colder one.
The second law of thermodynamics says that heat flows naturally from a hot object to a colder one. Heat will not flow spontaneously from a cold object to a hot object.
We'll be returning to the second law of thermodynamics because there are actually many ways of stating this law and it has many implications. An important implication and application of this law is the heat engine. So let's go there.
Section C, heat engines.
In the modern world, we're obsessed with energy. We need energy to power everything from our televisions to our blenders to our intricate mind control devices. That's why we're always looking for ways to obtain more and more electrical and mechanical energy. A heat engine is a device that turns heat energy into electrical energy or mechanical energy.
Another way to look at this is to say that a heat engine turns heat energy into work. These are extremely important devices, such as car engines and steam engines. And what would we do without our cars? Would we actually eat inside a fast food restaurant?
Let's look at how the heat engine works. There are two items required by a heat engine. First, a source of heat at a high temperature. Second, a body that's at a lower temperature, which serves as a repository or sink for the heat.
Imagine a source of heat that's so large that we can keep taking heat from it without lowering its temperature. This is called a hot reservoir. And if we can keep adding heat to the low temperature source without raising its temperature, then that's called a cold reservoir.
We'll call the temperature of the hot reservoir T sub H, and we'll call the temperature of the cold reservoir T sub C. The heat engine takes heat, Q sub H, from the hot reservoir and turns some of that heat into work, W. Then it dumps the leftover heat, Q sub C, which is now at a cooler temperature, T sub C, into the cold reservoir. So the engine is able to do work using the higher temperature, Q sub H.
Since part of the heat from the hot reservoir, Q sub H, became work, W, and the rest was deposited into the cold reservoir as Q sub C, we can say that Q sub H, the heat taken from the hot reservoir, equals W, work, plus Q sub C, the leftover heat dumped into the cold reservoir. Or if we isolate W, work equals Q sub H minus Q sub C.
We can evaluate the efficiency, E, of a heat engine by dividing the work output by the heat that's put in, Q sub H. That's E equals W over Q sub H. And if we substitute the equation for work we just found, Q sub H minus Q sub C, into the equation for efficiency, we get that E equals Q sub H minus Q sub C all over Q sub H. That simplifies to E equals 1 minus Q sub C over Q sub H.
Now that we've got the equation for efficiency, 1 minus Q sub C over Q sub H, let's do a problem.
Let's say we've built an engine that takes in 1900 joules and expels 1400 joules. What is its efficiency?
First, let's set up our information. The engine takes in 1900 joules, so Q sub H is 1900 joules. It expels 1400 joules, so Q sub C equals 1400 joules.
Remember, efficiency, E, equals 1 minus Q sub C over Q sub H. Now we can just fill in our numbers, simplify, and we get that E equals 0.26. We usually express efficiency as a percentage, so multiply that by 100, and we get that the engine has a 26% efficiency. Note that with a 26% efficiency, 74% of the heat taken from the hot reservoir does no useful work and is rejected as waste heat into the cold reservoir.
Okay, here's another problem. If an engine is 16% efficient and expels 4,200 joules, what is the work done by the engine?
Setting up the problem, we have Q sub C, 4,200 joules, and we've got the efficiency, E, is 16%, or 0.16. The problem asks us to find the amount of work done by the engine. From the equations we know, we've learned that work equals Q sub H minus Q sub C.